right. Good morning, everyone. My name is CJ Dudley, and today I'm going to be discussing dual-stage nanopositioner design. As a brief outline, I'll first give you guys an introduction to dual-stage systems, then discuss the design of a serial one-axis dual-stage nanopositioner, including the flexure design for good mechanical response, and some of the things that I found along the way, like preload shortcomings and new preload mechanism design and analysis to figure out what's really happening. And then we'll follow up with some conclusions. So as an introduction to dual-stage systems, well, first we need to backstep into single-stage systems. Single-stage systems have some limitations, especially in piezoelectric actuators. With increased range comes decreased stiffness, and with increased stiffness comes decreased range. So what if we want a system that has a long range and high stiffness for a high bandwidth? Well, that's where dual-stage positioning comes in. We can have the combination of a low bandwidth, long range positioner and a short range, high bandwidth positioner to give us both long range and high bandwidth. The simplest example of the dual-stage system would be just two of these actuators in serial, where we have the long-range actuator connected to the short-range actuator, and it basically acts as an arm and finger, if you want to think about it that way. So now that we have both actuators, we have to design a way to split the input signal for the actuators based on their range and their frequency capabilities. So range considerations. In AFM, we usually use a triangle wave to track. It provides a good raster scanning back and forth if you think about the input signal. So the triangle wave can be broken down into a Fourier expansion. And if we look at the simplest case where we split it based on the harmonics, which actuator is going to cover which harmonics. So in this case, we can say that the long-range actuator, here shown in red, covers the first two harmonics because he can only go to, say, 3K. This is just an example, right? Now, the short-range actuator, he's not really limited on bandwidth, but the range of the short-range actuator can only be 1.2 microns. So there's two metrics, basically, that we have to design where to split the actuator, whether the second or the third, or maybe even the fourth. So that's one way to split the actuator based on range considerations. The other thing to take into consideration is the frequency capabilities of each actuator. Just as a general rule of thumb, we want about a 10 times resonant frequency separation between the actuators. Now, why do we pick 10 times? Well, the actuators, if their resonant frequencies are too close together, each stage, then there is some sort of cross-coupling where one actuator's actuation can excite the other stage's resonant modes, and we get these kind of weird motions where, that are completely uncontrollable. So if the actuator is kind of assimilated to a second-order system, where we have a mass spring and a damper, the general transfer function in the S domain ends up being omega n squared over s squared plus 2 zeta omega n, which is the damping, plus omega n squared, where omega n is the natural frequency. And we want a 10 times separation of that. So if we plot a frequency spectrum on this, you can see that the long-range actuator is excited well in this range, but the short-range actuator does not have any gain in that area. Whereas over here, there's virtually zero gain for the short-range actuator, but a high gain for the long-range actuator, and a high gain for the short-range actuator. All right. So now, how do we design a stage to get these characteristics that we want? Well, first, we know that the first mechanical resonance needs to be in the actuation direction. Well, why? If the actuation direction is not the first mode, we get these uncontrollable modes, and that can harm a sample in atomic force microscopy. So the guiding flexures must be vertically stiff, stiff in the y direction, which would be this direction, and also in the rotational direction. This can be done by increasing the amount of flexures, decreasing the flexure length, increasing the height, therefore increasing the Z stiffness, or thickening the center section. So just as an example, if this were the first resonant mode and the sample were placed on top of the stage, right here, we would not be able to control this mode, and the cantilever tip could damage the sample. Now, if the rotational mode is the first one that pops up, well, then the sample is twisting and we aren't going to get a good image. But if the first resonant mode is in the actuation direction, there's low X stiffness, high out-of-plane stiffness, and we can provide good imaging. So for this dual stage design, we chose to do the design separately. And my fonts did not embed, but the desired low-speed resonance is around 2 to 5 kilohertz. And then if we take that 10 times separation, we want about 25 to 27 kilohertz. So the initial design gives us, this is the first mode in the actuation direction of the low-speed stage, and we have a 6.4 kilohertz separation of out-of-plane modes. So the out-of-plane mode occurs 6.4 kilohertz after the actuation mode. And then with the high speed, we have a 5.7 kilohertz separation. So good separation of the modes, looks like a pretty good design. But now they need to be combined together. Well, this combined design, as shown here in its fabricated state, is pretty small. But we chose this nested design because it minimizes the footprint and also allows the frequency characteristics of the previous design. Whereas, I mean, there is a bit of change in that some of the low-speed area is removed to make room for the high-speed actuator. But as you can see, the resonances are about 10 kilohertz separation, and same with the actuation. So good separation there. Now, once the stage was actually fabricated via wire EDM process and just some general machining, we chose to perform a frequency response on the system. Now, the low-speed frequency response looks a lot like what I showed you guys in the second-order system, where there's a nice resonant peak. There's a little bit of excitation out here, but it's well outside of the actuation. But then when you look at the high-speed frequency response, we get these out-of-plane modes. This is what this kind of garbage-looking stuff is, and we get this twisting, rocking, etc. And you can see that I began the inquiry into whether preload has an effect on this, and it looks like the flat and the ball preloads kind of give us a little bit more garbage than this large diameter flat. But it's really not desirable. It's a poor frequency response, really. So the initial hypothesis is that this improper constraint of the piezo actuator leads to the out-of-plane motion that's not really accounted for in this perfect world finite element analysis. So what does that really look like physically? Well, what's actually kind of happening is that the stage is only constrained by the bolt holes in the corners, and we get moving of the stage vertically, the stage body, and also the back end of the piezo wants to rock on the preload mechanism. So to investigate this further, we did a little bit of a preload constraint analysis. And what this is a single-point laser vibrometer was raster scanned along the length of the stage. So if we took it like this, we shot a laser down the center of the stage and did frequency sweeps at each one of those, and then correlated the points to a displacement. If you look at the ball preload, this one here, on the right you can see the frequency sweeping up, and once we get to about 10 kilohertz, the back end of the piezo starts to rock wildly, which is kind of interesting, and you can see that translates over to the stage in these kind of a Z motion. So we're actually looking down on it, and what you're looking at is a side profile. Now, if you look at the large flat preload, there is still a bit of Z motion on the back of the piezo, especially at these low frequencies. you can see that this is the piezo area right here, and he's growing as expected. And then once we get to about 10 kilohertz, the out-of-plane mode becomes pretty dominant, but the back end of the piezo doesn't necessarily move up as much. So there is this thought that maybe the ball preload is not providing a sufficient constraint on the back end of the piezo. So now the work has kind of accumulated into, rather than a single line scan of a laser vibrometer, we're going to raster scan a 2D area and try to provide an image to see if that's actually happening globally or if this is just kind of like a line phenomena. So we want to basically make a picture with the laser vibrometer. So we fabricated a 3D stage, so the laser can move in the X and Y directions, and scans are completed at each location and then accumulated. And the end result will be an image similar to what we see in the finite element analysis. Now, the parts have just been fabricated, and we're kind of getting the whole system up and running. So we're awaiting results, and hopefully by the end of this month, we'll have some conclusive results on that. So to conclude the talk today, we talked about high-performance dual-stage systems and their requirement for both good frequency range choice and the actual displacement range choice. The good mechanical design of an actuator or stage necessitates or gives low actuation stiffness while yielding high out-of-plane modes, and we can get this uncontrollable motion to disappear. And experimental frequency characteristics are quite a bit different than what we predicted in the computer model. So we're kind of having to go back and look at these preload constraints. So the preliminary results from the preload mechanism frequency sweeps are a bit promising to a conclusion, but more information is necessary. That concludes my portion of the talk, and I'll open it up for questions now. Yeah.
On your 2D raster scan, you'll essentially pick a point in the Y, and then when you evaluate the entire x-axis at every point, it seems like doing that sort of mesh analysis requires a lot of data.
Yeah, it does require a lot of data, and this whole system has been set up with a series of stepper motors so that we basically have a camera over the top of this stage. We'll design a scan area and say, what the interval of that mesh would be. And then basically it's a set it and forget it, kind of turn the lights off, and this thing does its sweep. Now, yeah, it's not the fastest, most effective way of doing 3D laser vibrometer scanning, but those units are pretty darn expensive, and our university can't really afford it. So this is my little my little way of making it happen. So, yeah.
How long do you think this scan will take you for that sort of?
Each single point takes about 25 seconds. So I think a good scan would probably be 100 to 200 points. But we do have a 6x6 scan area also, so we can choose a really large stage, like a dual axis. And I would imagine that would take upwards of maybe a night to complete. So, any other questions? Awesome, thank you.